Hello. So in this lecture, I wanted to give a introduction to behavioral Verilog. I will explain all about that. But first, I just wanted to show you. So here I have an implementation of Flappy Bird, the game. This is actually the same assignment that I used for CSE 111, and which I'm actually teaching again next quarter. It is an advanced C++ class. And in this class, you will have to design an emulator to get this game file working, which is flappybird.slug. Here's the source code for this game file, but I will run this game file. And now it just opened this window right here, and we can see that currently nothing is happening on screen. So this is currently representing Flappy Bird, kind of like the intro title sequence. And then as I now start to jump, then now the game begins. And when I jump through things, well, I didn't quite make it. But you can see that now I've entered a new game state, and this game state looks like I've died, unfortunately. But I can restart. So this is like the playing game state. And then, but as you notice, so once I hit a wall, I'm not actually able to jump anymore after that. So that is probably like the falling game state, or maybe like the dying game state. So there's multiple different game states. And I just wanted to show you this because I feel like this is a really good visual on kind of why state machines are so important. It turns out that when writing basically any software that like in game development or in embedded systems or for robotics, mechatronics, all the time you are constantly writing state machines. And definitely also for game development in this case, because we have all sorts of different states. Here's the source code for this program, for this game, and we can see that I have the waiting state, I have the flying state, I have the dying state, I have the dead state. And you can see that I'm using an enum, just like the enums that you are also allowed to use in System Verilog, as was mentioned in the last lecture. So enum, so we have all these different states right here, and I can even look at where this state exists, and if I go down to it, so I think where is it? It's right here. Yeah, so I have the state update function. And inside this, I have this switch statement, very similar to in System Verilog. You would use probably a case statement. And then inside this, we can see that we have all of these different cases. And in a C program, obviously what happens is you run each line sequentially. Like first you check like, okay, are we in this state? No, okay, let's go to the next line. Are we in this state? No, okay, let's go to the next line. And then, it's running each of these lines. And so the behavior of this code is like very clearly like whatever, it's just running like each line one after another. And so it's very human readable. Like we can just kind of look at it. We can see like, okay, if we're in the dead state, then like if we press the A button, then now we want to set the new state to flying and we want to run all these functions. Or if we're currently in flying and the bird touches the ground, then that means that we immediately die or something. So there's it's a very clear demonstration of how you have one state, and then depending on whatever the user input is, you can then transition into whatever the new state is on like the next maybe frame or the next clock cycle or something. And it's exactly like that in Verilog as well. So I wanted to I just now wanted to pull up some code that I've written. So right here, so this is just the linear algebra unit that I'm currently writing for my research. And we can see at the very top of this, we can see that we actually have this state enum right here. And so we have all these different states that we can have. So waiting for input, squaring, averaging, loading for divide. It doesn't really matter exactly what each of these states mean, but what is important is that, we can see that each of these states are now used down kind of here in this big block. And this big block is very similar to the type of coding that you would expect in a C-like language. And like you're probably looking at this and you're going like, wait, what? Like you can use like if statements and like this just looks like I'm writing like C code. But this is Verilog. Yeah, it's like you can see, this is a .system Verilog file. It turns out that you actually can use if statements inside of Verilog. And that means that now your Verilog will be extremely readable, just as if you were just writing like C code. And so yeah, in this lecture, I just wanted to quickly explain maybe the reasonings for this, and then also what that actually means when you transform this behavioral high-level Verilog into a lower-level netlist. Yeah, cool. So I also just wanted to pull up a couple other examples right here. Yeah, just to kind of really nail it in. So here is CVA6. CVA6 is one of the most popular open source RISC-V CPUs. And you can see it's all written in System Verilog. This assembly is just for testing. So primarily all of the code is written in System Verilog, and whatever you can take CSE120 and you can learn about all of the different steps inside of the CPU. But it's a fantastic code base on Verilog organization, because this is one of the largest Verilog projects, open source Verilog projects that exist, and therefore it needs to be very organized and cohesive. And so because of that, they have elected to follow extremely closely the low risk coding style. And so if we pull up now, so in CVA6, so if I pull up the file I was just looking at, which is the load unit, whatever this does. But we can see that, very similar to the code that I wrote, we can see that it has state D, state Q, and it has all of these different states, and this is using an enum. And then later I can look at where state Q is used, and okay, yeah, so it looks like there's another like always comb block. And then we have this case statement where we take in this case Q and we say, okay, so if we're in the idle state, then run this line, and if this if statement is true, then run this line. And and so this is CVA6, a CPU that has been taped out hundreds of times, if not thousands of times. It's one of the most popular open source CPUs that, like, if you wanted, like, you could go out and actually put a CVA6 core inside of your own chip if you wanted. ETH Zurich is at the university that is like primarily trying to work on an open source flow for that. Anyways, okay, it's a very cool code base. Highly recommend looking through it. But they follow the low risk coding style guide. Low Risk is a company in Cambridge, England, that is known for being an open source company that actually tapes out chips. So all of the code that they endorse and that they write is going to be really high quality stuff. And and we can find where they recommend what they recommend for state machines. And so this link right here, I actually provided in your lab document this quick little write-up on finite state machines. So I highly recommend that you read through this. It's really useful. Like I said, Low Risk, they've taped out thousands of chips. They're a really reputable company. So basically any advice that they give, you should honestly really thank them for the advice and all the time that they've spent, because it's honestly just really good advice following their style guide. And we can see here that they recommend having an enum with underscore D underscore Q and always com block. And then also at the very bottom they have now your basic always FF that puts the D signal into the Q signal, and then also sets whatever the reset value of your flip-flop should be. Okay, cool. So now I want to just kind of briefly go through an example of how to go through something that looks like this and then produce a netlist, because it turns out that you can actually just plug this into digital.js and you can get back like a full mux circuit. And I can even show you that. Give me just a second. Yeah, so I can show you this. So here is actually, I believe this was a question on last quarter's homework, and so the question was take this file and draw out a circuit schematic for it. And yeah, and you can see it's just like a bunch of if statements and whatnot. And, it's a little bit confusing. Like you have if statements after if statements. And but let's see what happens when we try plugging it into Digital.js Online. Okay, I'll paste it in. And there we go. Okay, so yeah, so very cool. So it does actually synthesize to a full circuit. And we can see that actually, so each one of these if statements right here, they actually represent a different mux, right? Because an if statement, I mean, it's just like, if it's true, then probably like take like the true path on the mux. If it's false, then probably take like the false path on the mux. And yeah, it's very similar to just using like the ternary operator that I'm sure you've seen. Like when you do whatever, assign a equals like condition, question mark, and then whatever, true case, false case. Yeah, like for example, like here is probably what you ended up writing for your VGA timer module for lab 3. So yeah, like you can see, like usually you have this conditional operator right here, so question mark, and you say like, oh, if this condition is met, then true case, otherwise take the false case. Yeah, it's the exact same thing with if statements. You just kind of go through, and you're like, okay, so if this condition, then go and put a mux there. Else that condition, then put that in the false case. And then you can also have nested if-else statements, where now you put an if right before a mux, and that now means that now you have like multiple muxes now in series. Yeah. So okay, let's actually kind of go line by line through this example, just because I feel like it's a little bit confusing to look at all of these different muxes and try to make sense of it. So let's actually try to just go through this by hand. Okay, so yeah, on the left here, you can see the always com block that we will try to synthesize. And then on the right here, we can see my iPad screen. So the first thing that I notice when I look at this is we can see that we have a bunch of signals with _O. And hopefully you remember what _O means. _O denotes that these are outputs. And that is different from _I, which that denotes that this is an input. So what we're doing is we're assigning our outputs depending on what the inputs are. Yes, okay. So inside this always com, it looks like we have several outputs. So we have X. Let's just make a quick note of all of them. So we have outputs. So we have XO, YO, is that it? Oh, and then ZO down here. Okay, so those are all of our outputs. And what are our inputs? Let's see. So we have D, A, B, probably a C somewhere. Yeah, okay, so it looks like we have A, B, C, and D. So let me just write that out. A, B, C, D. Okay, and so what that is going to mean is there's actually going to be 3 whole separate mux trees that we will be creating, because we need a different mux tree for each one of the different outputs. Even though this is one single always com block, this is called a procedural block, because you can think of it almost as like we're running like this procedure of like each line of Verilog could be considered to be like run one after another. Of course, Verilog isn't actually run when you synthesize it. It is instead just generated into hardware. But yeah, so therefore, yeah, we will have 3 separate mux trees that we will need to draw. So let's look at you know what, let's do this first one here, Z. I think this will probably, no, actually, sorry, what is the easiest one? Yeah, we'll do X first. Okay, great. So we can see up here that we have this default value. Let me make that note. So default value of 0. This just means that if we ever have an if statement that maybe has a true case but not a false case, or maybe a false case but not a true case, this means that just no matter what, it will default to the value 0. meaning like, yeah, if we get to the end and if for some reason we never took any one of these paths here, and maybe like x was never set, this just ensures that like the default value of x is 0. Yeah, and similar with z. Okay, so I'll just copy that over. Yeah. Okay, so good. So I don't think we really need to worry about the default value yet, but maybe the first thing though is, I mean, we have an if statement right here. So let's draw out a mux. And remember, so the output eventually is going to be x out. Okay, and it looks like the select here is a. Okay, and then the true case, well, it looks like if the true case is taken, then x is going to be 1. So, okay, so true case, x will become 1. But if the false case is taken, well, then actually it looks like there's a whole nother kind of mux that needs to be inserted here. We don't actually know immediately what is going to happen. So, okay, so let's insert now another mux here. So this is the false case. And now we have this new selector. So this new selector is C. So C of I. And we say, so if C of I is 1, well, in that case, then we can see that x is in fact set, and it is set to D. Okay, cool. But we don't have an else statement on this. So that actually means that, yeah, this signal right here, the signal that is, since there's no else case, means that this path is unset. So therefore, we just go back up to this default value right here, and our default value is 0. So I will just write in a 0 for this path. There we go. So that is now x completely drawn out. Yes. So hopefully this makes sense. So maybe pause this lecture, go back and make sure that kind of procedure makes sense. But now I'm going to move on to y, and I'll move just a little bit faster now. Okay, so y, good. So it looks like it's going to be honestly very similar to a. Sorry, it's going to be very similar to x, right? Because we have a mux here that will still assign it. Yeah, we still have a mux here that uses a as the select, except now y is the output, and when a is set, instead the value becomes 0. And then for the false case, once again, the input is C. So Ci, and so here we have that if C is set, then we are set to D. Okay, so D of I. But then also notice that we have this new value right here for B. So if C is 0, then we will not take this if statement. So therefore, y will actually be equal to B, it looks like. Okay, yeah, so notice that kind of interestingly, the x case used the default value versus the z case. My mistake. Okay, sorry. Notice that the x value used the default case, the default value of 0, but y did not have a default value of 0, but it's okay because every single path ended up being set. So in here, so these paths were set, and then that path was set. So we're all good. Okay, and then now I will set z. Okay, so z, we can see is set right here first. Let's go and make that mux really quick. So we are going to have, honestly, yeah, kind of a similar thing. So we have like if a, if I, and then we're saying if it is 1, then, well, then we probably just take this default value, which is right here. So that will be now 0. And if a is 0, then now we take this case right here, which is just going to be another mux. So I will draw another mux, and the selector is C. And now if C is set, then now Z is going to be 1. So if it's set, then it's going to be 1. If C is not set, then we go all the way back up to our default value. So once again, we set this to 0. Okay. But then notice that actually down here, we have 2 more checks. So we have this check, if B is set, then whatever happened up here, actually just ignore it and now set Z to A. So that kind of means like you can kind of think of it as in like, if you ever have an if statement that happens later than another if statement, then it becomes like the more important mux. So actually let's work backwards on this, because so it looks like this is going to be the most important mux. Like it doesn't matter what anything up here says as long as D is set, because if D is set, then Z is just going to be B. So okay, so this is kind of the most important mux. So let's draw this out then. So okay, so if we have this mux and D is the select, okay, and if D is 1, then we are set to B of I. But if D is 0, then actually we go back up to whatever the most previous thing was. So now we draw in a new mux, and this mux has an input, a select of B. Okay, and we say that if B is set, then now we grab A. But if B is not set, then now we just grab whatever the value was from the previous kind of mux tree. Okay, so if B is not set, then we just go all the way back, kind of like that. There we go. So there's a line of 4 whole muxes just for Z down here. Yeah. Okay. Yeah, this one's a little bit confusing. Just so yeah, let's look through it one more time. Okay, so we have the most important mux is this last one, so it's right here. But we're saying if Z ended up, if D was not set, then we go back up to the next mux. So now we look at this mux, so we can see, so if B of I is set, then now we grab A of I. But if B of I is not set, then now we go to the previous mux. And so this previous mux now, well, we see that if A of I is set to 1, well, then Z is not set. But if A of I is 0, then now we take this path right here, which once again has another mux. And this other mux says if C is set, then now Z is set to 1. And for every path that was not clearly specified, so for like A, we didn't specify a value of Z. And then also for not C, we did not specify a value for Z. So therefore, for both of these two cases, we can see that we use the default value of 0. Okay, cool. Hopefully, this kind of makes sense. It's a little bit overwhelming the first time you look at it, but that's why I wanted to make this a recorded lecture, just so that you could actually look at it. I also want to quickly mention one final thing. So let's see what happens if I now pull back up digital.js. Okay, so here's digital.js. And so if you remember, so these default values right here, these were quite important because they ended up specifying like what would happen if we didn't actually explain what was going to happen in specific steps of our tree. So like right here, like we didn't actually specify what we wanted to have happen, so it just used whatever our like fallback default value was. But let's see what happens if we try to remove this value. Maybe try to guess like, yeah, what would happen if we tried to remove that. So I will just kind of comment out both these lines and let's see what happens. So if I hit run, and you know what, I'm also going to change this to that. I won't tell you what that does, but okay. Okay, so there we go. So it's synthesized, but actually it looks very different, right? It's actually, there's only a couple muxes here, and the muxes actually just drive Y. which is interesting, right? Because y was the only thing that didn't have a default value to start with. So it looks like the logic that assigns z and y are completely different. And kind of the biggest thing right here is you can actually see this new symbol right here, and it kind of looks like a flip-flop, right? Because we have D and Q, but instead of a clock input, it actually has an enable input. And and kind of, so the reason for that is, so this is another type of memory device, and basically what it does is, like, instead of worrying about the clock edge, now what it does is, like, anytime this enable signal is activated, that means that now D should be sent into Q. But whenever enable is deactivated, so if enable is in this case, it would be set high. So if it's deactivated, then now Q will be latched at whatever value it was previously at. So yeah, you can, I guess, kind of think of it as like a door latch. It's just like is it latched? Is it not latched? Versus a flip-flop, it's like, okay, at this time, everything like shifts over. And then you wait for the next clock pulse, and it's like, boom, okay, at this time now everything shifts over. Versus with a latch, it's like, are we latching it currently, or are we unlatching it so that now data can pass through? Okay, and the reason for that is, well, if we don't specify a default value, then what we assume is that the values of x and z will take on whatever value they stored most previously. And yeah, it's a little bit confusing. I'll say it again. So if we do not specify a default value, then x and z will take on what value they were most recently. And and yes, maybe take some time and think about that. But basically what this means is that now we're going to have weird timing constraints, where now we need to worry about things between clock edges. Now we need to worry about, like, kind of glitches and whether, like, something goes high for just a second, and like what changes happen. So therefore latches, creating latches like this are actually generally very much frowned upon. And actually in 2005, the IEEE standard introduced something called always comb, which replaced this older standard. So this, before always comb, we had at star. What at star would let you do is it would let you make like latches like this. But then IEEE now added this new always block called always comb, and this forces everything to be combinational. So now when I hit run, in combinational meaning no memory. So now when I hit run, you can see that actually we get an error, and it says like, oh, latch inferred. And the reason why we get an error is because this is not creating, like, this always com block is no longer creating combinational logic, because now we can think of it, now it needs to keep track of like what the most previous value that it was. So this is no longer combinational logic. So we get an error, it says latch inferred. If we want to fix this, then now we just have to re-put this back, and now this will make sure that we don't need to care about whatever value x and z were most previously. Now we can just say, no matter what, it's going to have some sort of value assigned in its like mux tree. Like in any single step, it will have a fallback value to use. So now when I hit run, now you can see that it's all working. And it also kind of an interesting thing. So yeah, here you can see z, and we can actually hover over each of the little muxes, and it will tell you exactly which mux each, what each if statement each mux belongs to. Okay, cool. So I think that is a good place to leave off. Just wanted to kind of give you an intro on behavioral Verilog, because you will need this for your lab. And I also just want to make a quick note that if statements are also very similar to case statements. I didn't go over case statements in this lecture, but I trust you to be able to read through the low-risk coding style and understand how to use case statements correctly. If you have any confusions on case statements, then I recommend trying to Google things on them, because yeah, this is the style that I highly recommend you use to implement your lab for. Yeah, the alternative to this would, of course, be implementing all of your muxes kind of this old way, using assigns and the conditional operator. One nice thing about using assign and conditional operator is there's no chance of you accidentally generating any latches. So in some ways, this may be more preferable because now you don't have to worry about any latches, but it also means that this is a little bit less readable versus actually typing out like what happens. Like you can think of like what happens at every single line in your Verilog. So, okay, cool. I hope this all made sense, and I look forward to seeing you soon.